Good afternoon, everyone. Hope you're having an incredible day at Next so far. Welcome to our session, Build and Scale AI Infrastructure with GKE, Kubernetes Engine, and Hyperdisk. My name is Sajal Agarwal. I'm one of the product managers here at Google Cloud. Today, we are joined by an incredible group of global technical leaders who are pushing the boundaries of what's possible with AI and our computing infrastructure. But before we dive into the panel, I want to set the stage of our discussion today. We are going to move beyond the high-level discussion and get into real-world engineering and business decisions that enable these organizations to serve millions of users with near zero downtime. Please feel free to take pictures as we are going to share some amazing content, including architectures. So just to summarize a little bit, what is Google Compute Platform for us? It comprises of GKE, our Kubernetes Engine, and Hyperdisk that is built on the three pillars being workload optimized, TCO efficient, and enterprise ready. These pillars ensure that we can meet the most demanding infrastructure requirements while delivering superior economic value. At the heart of this is our Titanium offload engine, which is the purpose-built hardware accelerator. It allows us to offload management and I/O tasks, freeing up cycles for your actual workloads. So whether you need general purpose power or specialized AI infrastructure, we provide a flexible environment that spans across GKE and GKE, ensuring that your enterprise-ready applications can scale seamlessly without compromising performance. Double-click a little bit on the workload-optimized compute. Google Cloud offers a wide range of compute families to cater to both general purpose and specialized workloads. We have enterprise compute with the C series that delivers consistent, predictable performance and advanced maintenance controls. We have N series that provides flexibility and optimized for price performance and optimizing for TCO. It is suitable for running most workloads. We also have the compute optimized for the high performance computing, the HPC workloads. We are also introducing a new family of VMs, the CN and the M series in preview that leverages Titanium adapters to deliver industry-leading throughput and 95 million packets per second for data-intensive workloads. Finally, we have a range of accelerator optimized instances that deliver towards the AI hypercomputer architecture. At the bottom, you see Hyperdisk, which is fundamental for all our AI workloads, allowing independent tuning of capacity and performance. So you only pay for what you need, a perfect example of being TCO efficient. For me personally, what's really inspiring is the outcomes we enable our customers to deliver to their customers, which are customers across industries and people around the world. And we are going to hear some more use cases from our panelists today. Some of the examples, for example, a retail customer running critical workload on our computing platform, enabling millions of small businesses to expand reach. In clinical insights, healthcare customer training and serving pediatric-based LLMs, transforming pediatric care with AI-driven clinical insights. In the field of drug discovery, a customer is running HPC workloads for their R&D on Google Cloud. In the world of transportation, customers are running ML workloads using Google AI Infra. In fraud detection, customers are using compute infra to safeguard organizations. Finally, my favorite, real-time entertainment, customers are now serving their latest AI DJ features on our TPUs. With that, let's dive deeper in some of the specific use cases and the business outcomes with technical enablers with our panelists today. Without further ado, please join me in welcoming First off, we have Vinicius Rosse. He is the head of information at Kuala Saudi, and he's traveling all the way from Brazil. Second, we have Nagesh Sahu. He is the senior staff engineer and traveling from InMobi, India. We have Mr. Atakan Sengoz. He is the backend developer lead at HubX, joining us from EMEA, Turkey. And finally, we have Mr. Deng. He's the director at NetEase Games in China. So truly a global panel sharing their use cases today. And feel free to take pictures. As I said, we are going to get started here. We can get started with InMobi. For example, Nagesh, why don't you take a moment, tell us who you are, tell us about the journey that you took with Google Cloud, with the infrastructure that you utilized, and some of the results and the architecture with the outcomes.
Thank you, Sajal, for the introduction. I'll take a moment to tell about who we are. So if you have ever seen an ad on your smartphone while using an app, or while streaming something on your smart TV, or while browsing anything on your desktop, there is a good chance that you have already experienced something that we have built. You just don't know it yet. InMobi runs one of the largest omni-ad platforms in the world. Think of us as a marketplace connecting two different sides of the world. On one side, we have publishers, which comprises of app developers, CTV platforms, website owners, which own screen real estate, and then they want to monetize their audiences. On the other side of the world, we have advertisers and agencies to whom brands reach out to drive app installs and increase consumer awareness. We sit in the middle to make that connection happen in real time at scale. And when I say scale, I'm not exaggerating, I mean it. We process close to 250 billion requests in a day. We have strategically placed our data centers throughout the globe so that we are able to serve any ad request with low latency possible, while our fleet simultaneously scales up and down based on the user traffic. Right? As a senior architect at InMobi, I live at the intersection of the scale, challenges, and the cloud. We leverage Google Cloud end-to-end, starting from network layer to compute layer, and all the way to the storage layer. Privileged to be here to share our learnings with you guys. Thank you.
Thank you for the introduction, Nagesh. Moving on to NetEase Games. Deng, would you like to share something about yourself and the company, please?
Thank you. Hi, everyone. Deng from NetEase Games. We are one of the largest gaming company in the world by revenue. So most of that currently comes from our domestic market in China. However, we have a major long-term goal that we want half our revenues to come from international market. Games like Frapunk and Deng City Dynasty are great examples of our recent global efforts. We even have an AI native game in the works with the Gemini team, but we are not ready to dive into that today. So if you look at the diagram on the right, you'll see our typical game server architecture. We use it to deploy everything on standard virtual machines. But as our player base grows, we hit some roadblocks. The biggest issue was scaling lag. Traditionally, server provisions was just too slow. We also struggled with latency. Since Frapunk and Deng City Dynasty are fast-paced competitive games, players are incredibly sensitive to even the slightest lag or jitter. To fix this, we teamed up with Google Cloud. We moved to their latest computer instances for better raw performance and adopted Google Kubernetes Engine for rapid elastic scaling. We also started using live migration, which allows us to do maintenance with zero downtime. The result has been huge. We have gone from hours level scaling to just minutes, and this also saves us a lot of money because we can now scale precisely based on real-time demands. Combined with Google's global network, the player experience is much smoother, and we are seeing a very positive response from the community. Thank you.
Thank you for that. And we are going to dive deeper into some of those details later. Next up, we have Kaala Saude. Please go ahead. From Brazil, we have Mr. Vinicius from Brazil. Yeah.
Thanks, Sajal. Hi, everyone. It's a pleasure for me to be here with all of you, having this opportunity to share this panel with some of good friends. I'd like to start by saying my name is Vinicius. I'm from Brazil. I'm 28 years old, and I'm the head of information at Kaala Saude. My biggest responsibility basically today is to fill the gap between the business necessities, the business demands, and the technical solutions. So nowadays I lead the tech, data, and design product teams. We are a Brazilian B2B telehealth startup that offers a lot of different product services for schools, okay? We have psycho products, mental health products, nutritional products, and the most used product by our customers is the one related with the telehealth service. We have more than 25,000 students in our platform and more than 150 schools using our platform. And basically, I'm here today to share with all of you because 100% of what we built in terms of infrastructure, we built by using the GCP products. And over the last months, we launched basically an AI-powered transcription tool to make faster some of the most important processes developed by our doctors and nurses. I'm talking about the documents, health documents generation processes. So it's a pleasure for me to be here today, guys.
Thank you, Vinicius. Finally, we have Mr. Atakan from HubX.
Hello, everyone. I am Atakan. I am working at HubX as backend lead. In HubX, we built mobile and web application at scale, and we have over 300 million users, downloads, and across more than 30 apps. And our portfolio includes AI-powered mobile and web apps. Also, we have some context-driven applications. But a big part of focus today is on real-time AI experiences, near real-time AI experiences. And I can share some tech stack from HubX for you. Our development team includes React Native, Flutter, web frontend, native Android and iOS teams, also backend, machine learning, data, and DevOps teams. So we use priority pool compute classes to switch between spot on and on-demand machines if it is available. So we automatically, and we optimize our models with PyTorch for GPUs and Trillium TPUs. We are using Trillium TPUs, which is great. So we use cloud storage, Hyperdisk ML, and file store to access our data stack with high performance and low latency. So overall, we develop these apps with these teams and technologies, and also we focus on scaling AI systems in production environment, and especially around near real-time AI experiences, inferences, and large model serving, and making sure we can deliver fast and personalized AI-based results for our customers, and with high loads, under the high loads, and under the high traffics. I think I summarized myself and HubX. Thank you, Sajal.
Thank you, Atakan. I think this helps set the context for people who do not know about the customers and what they do. I think with that, let's dive into the discussion today. First off, Nagesh, you talked about millions of requests per second, daily. So how has moving to a unified infrastructure on GKE and CN instances changed your approach to manage that large scale, infrastructure while managing the volatility, especially during peak events like the Black Friday events?
So before I answer that, it's very important to understand what problem actually felt like. So we had the same stack running for years, but the world around it kept growing. We were onboarding more partners, which were pumping more supply to our systems. But it wasn't just the traffic. The CPU cost per request was growing too, because of a lot of ML inferencing was baked into each ad request. Now, we had a simple architecture where single instance family was powering all the regions, all the clusters, all the node pools spread across zones. This is simple and predictable, but at our scale, this has become a limit. What we needed was to have a resilient and a distributed solution. Then when I came to Cloud Next last year and heard about how AppLovin has navigated their BFCM event with the help of GKE compute class, it clicked immediately. So instead of pinning a single instance family to your fleet, you can define a priority list. GKE does the scheming over that and provision the best possible node for you, ensuring you have resiliency. Now, we were totally relied on N series, but when Axon C4A came into picture, our initial benchmarks demonstrated 30% price performance, which is not marginal, and it's different shift in our unit economics. But deploying multi-processor architecture in production at scale was non-trivial, and it demanded a lot of changes across our stack. 3 things I would like to highlight. The first one is your application needs to be hardware agnostic. In our application, there were several areas. For example, SIMD Java, which we use for JSON parsing, was not compliant with ARM. We needed to rewrite those pieces to make it architecture neutral. The second one was, for the longest period of time, all of our nodes were exhibiting similar throughput. Based on that assumption, we developed several local algorithms. And the moment we introduced heterogeneous nodes, the local algorithms started exhibiting skewed behavior. So we introduced performance profile as a feature to those local algorithms so that they operate as expected. The third and the most important one is the developer experience. We need to get this one right. We enhanced our CI/CD and canary verification to accommodate multi-architecture as a first-class citizen so that every feature that we ship is being validated before it gets promoted. So we were lucky enough to roll this out before our Black Friday Cyber Monday event, and we saw the biggest system scale ever, 8 million QPS per second, powering more than 50 million inferences per second, pushing 300 terabytes of data to Google Cloud Storage. And honestly, this was something that we were not able to think of earlier. So instead of trying to control the volatility, we tried to build a system to absorb the volatility. That's how we approached.
That's a fascinating perspective, not just on solving volatility, but on scale as well, the numbers that you shared. Thank you so much. Shifting gears a little bit towards the gaming world. In competitive gaming, latency is the ultimate tax. So why did you choose our C4 and 4 instances to solve for the player latency?
So for us, the decision came down to just one main factor, and that is the single core performance. In the world of game as a service, we actually prioritize single core performance over having a high number of cores. You might wonder why. That's because most modern game logic is still largely single-threaded. This means that tasks like physics calculations, play movements, and heat detections usually happens in a sequence in one core. If that one core is slow, the whole game experience is slow. For the players, low single core performance leads to higher latency and less responsive games. In competitive titles, even even a few milliseconds of delay can be the difference between winning and losing. So if the server can't process the game logic fast enough, players experience stutterings or lag, which really hurts the user experience. This is why we were so excited about Google's C4 and N4 instances. These latest generations of a significant boost in single core performance. And by moving to this hardware, we have been able to reduce our server response times and handle complex game logic much more efficiently. So essentially, it allows to provide a much smoother, snappy experience for your players, regardless of how much is happening on screen. Thank you.
Thank you. It's clear that performance is paramount there. Now, Vinicius, Koala, how they migrated from AWS and Heroku. So can you tell us a little bit about the journey, migration, as well as the partnership that helped with your pediatric telehealth solution with Google Cloud?
Yeah, for sure. In 2025, we faced a significant operational challenge in the company. The volume of telehealth requests of our platform grew by 65%. And obviously, that's something good for the business. But at the same time, it exposed a critical bottleneck on our workflow. So it was something that was simply not scalable. Our doctors and nurses were spending a substantial portion of their time basically producing lots and lots of manual documents and health records. So if we could change the way they work and their routine to make them able to spend more time taking care of patients, looking after our students, that'll be something good for us, obviously. So basically to solve that kind of challenge, we turned to Google Cloud. And now I'm going to give you some context about how this decision came about. Originally, 100% of what we had were running on Heroku. And at the time, our next logical movement was to migrate all that we had from Heroku to AWS. But midway through the process, we're accepted into the Google for Startups program, and that changed basically everything for us. Now, we receive basically $100,000 in credits to spend in the GCP to build our infrastructure, and we also have access directly to the Google technical engineers. If we combine, for example, the financial assistance we receive with the guidance offered by the Google technical engineers, our decision to start to use 100% of all we have in terms of infrastructure in Google and the Google workspace by using GCP became easier. And from there, there are three pillars that define our technical approach when we decided to make this movement. The first one, I would say, is the scalable compute. When we started to produce and to design our infrastructure, we divided all of our services into different nodes. So nowadays, we have five node GKE run production clusters, and we divided all of our applications into different because we desire to have our customers never fully exposed to a single one, because if one node goes down, we're going to have another. And we also implemented in our system an auto scales to avoid any kind of human intervention if, for example, our infrastructure needs to expand. The second thing I would like to say and share with you is the one related with the data privacy and data security. Given that we handle with personal data and health data, we need to be aware about we're going to store all of this content. So that's why we choose to use the Google Cloud Storage with some backup, some lifecycle politics, and that's why we start to use the GCS. And finally, we need to talk about the AI environment provided by the Google Cloud Platform. Basically, all of our features, in all of our features, we use the Google APIs combined with the Vertex AI running Gemini to automate the most part of our manual processes. That's it. Thanks.
Thank you very much. That's a great example of the human impact with AI while preserving the privacy in a regulated industry like healthcare. So thank you very much for the partnership with Google Cloud. Moving to you, Atakan, you deal with 40 GB models that take around 30 minutes to load earlier. So what was the aha moment that led you to choose AI hypercomputer stack with Hyperdisk ML?
Okay. Behind the scenes, some base models quite large, around 40 gigabytes. And when during traffic spikes, many pods need to start at the same time, right? And each pod loads this model into GPU memory. And before Hyperdisk ML in our previous setup, starting time around 50 to 60 pods could take up to 30 minutes. And it was huge, and that created two main issues, two critical issues for us. Firstly, users were waiting, and secondly, GPUs were sitting idle, which means we are wasting money for nothing, and we had bad UX, right? And at first we thought this was a compute issue. We needed bigger machines, more GPUs. And after digging deeper and deeper, we realized that something important for us, it wasn't compute, it was I/O. Our workloads are extremely read heavy, and the storage layer became the bottleneck. So that's what led us adapt to AI hypercomputer stack and Hyperdisk ML, which allowed us to handle that concurrency efficiently and remove the bottleneck. Thank you.
Thank you for sharing. That's a win-win situation. I want to get a little bit more under the hood for our audience of technical folks and architects. Let's talk about specific design patterns, if we can. Nagesh, you run 90% spot instances on GKE, which is massive. Can you share some specific design patterns, especially that allows you to have near zero downtime around the peak events such as Black Friday, Cyber Monday? For example, like how your Java applications handle eviction notices.
So as I said, our incoming requests are dictated by the end user interaction pattern with the apps. So we didn't have any way to predict the incoming traffic. There might be several ways, but the reason we were not able to leverage CUD is that we won't be able to utilize them properly. Now, the question was not whether to run spot or not. The question was, how do we build a system so that eviction is treated as a normal operating condition instead of an incident? So we already had a starting point with GKE and custom compute class where we defined a spot node pool as a first priority and then on-demand node pool, which can be scaled later on. But that was not sufficient at our scale because we know burst evictions are brutal. And when they hit, we want remaining part of the fleet to hold the line until the replacement comes up. So we did two things. So first is having the headroom in the HPA. So it isn't a slack, it's the buffer which allows us to absorb the burst traffic, or maybe if your part of your fleet is degraded, the HPA is able to handle that. We run x86 at 60% HPA, whereas we run C4A at 75%. And the reason for that is the C4A is SMT disabled, meaning there is no overhead of doing context switch, and we are able to get good latency there. We were able to run the system sufficiently with that. But then when we observed, when several nodes are coming up, we saw there is a delay in the startup time. Then we scanned the whole ecosystem. So we know first GKE scans your node pool configuration, then there is a node provisioning which happens, then it pulls a Docker image, then container startups throughout the series of events. We tried to optimize each and every layer, and that's where GKE image streaming helped us immensely by shaving off 50 seconds in the pod startup time. We were running good until we were hit by something we didn't anticipate, cyclic evictions. So cyclic eviction is a situation where a part of your fleet got evicted and then you received several other nodes. But after a certain amount of time, those nodes also get evicted, resulting into your fleet getting into a limbo state. So this pushed us to think harder. What we devised was a solution on top of GCP Compute Spot Notice API. So the centralized system will listen to this API and operate at 2 layers. The first one, application layer, to drain the connections and honor the in-flight request. And the second is at the infrastructure layer, where it just does the bookkeeping and operates on several thresholds. For example, if 10% of your fleet is degraded, it will automatically patch custom compute class to on demand, ensuring that your system is stable. And once there is a cooldown, we again revert it to the spot. And honestly, we got here through several incidents and sleepless nights. But at the end, we had a solution which automatically heals our system without any manual intervention. With that, I would like to leave you with zero downtime, near zero downtime with Spot isn't a configuration, it's a discipline. We applied first principles to understand our workloads from a breadth and as well as depth, understand our bottlenecks and resolve them one by one. And that's kind of engineering challenge that keeps us honest and keeps us learning. Thank you.
Thank you, Nagesh, for sharing that. Efficiency at that scale is incredible. Deng, staying on the topic of uptime, it is really important from a gaming perspective that the sessions are stateful. So how do you pair GKE and live migration with the global backbone to prevent maintenance-related any service disruption for real-time competitive play?
Sure. In gaming, the biggest challenge is that our sessions are stateful. So this means if a server goes down, even for a second, the player's match is ruined. So to prevent that, we use a two-layer approach. First, on the hardware level, we rely on live migration. This is a huge win for us because it handles the unplanned maintenance or hardware failures. Google moves our running virtual machines to new hardwares without a reboot. So this happens behind the scenes, so our games stay online and the players never even notice. Second, to the application level, we use GKE to handle unplanned maintenance and updates. We have built a custom scaling strategy where we don't just shut down pods or servers immediately. Instead, GKE waits for the player session to finish naturally. So we only let a pod exit once the last player has completed their match. So by pairing live migration for the hardware and the GKE for smart scaling, we have managed to make our maintenance almost invisible to the player. So it allows to keep the server running smoothly without even kicking a player out of a game.
That's a seamless experience for players is key. Vinicius, looking at your setup, the production cluster is quite lean at 5 nodes. So how do you manage high availability for real-time medical processing while keeping the costs low and keeping it efficient?
Okay, let's go. So when we talk about high availability in a clinical environment, we need to be aware about some concepts. For example, predictability and also resilience. So when we started to build our infrastructure, we did it by following some important aspects I'm going to share with you, okay? The first one is the concept of infrastructure as a code. So 100% of our environment is declarative. It means that by using Terraform, basically, we're able to replicate all of our environment. We're able to recover it from a disaster if something happens, for example. And we also can scale to another region. And we can do all of it basically almost instantly and with few comments, for example. That helped us a lot when we need to manage our GKE environment. The second thing I like to share with all of you is the workflow isolation. So Basically, we separated all of our AI have processes from our core services, because if at some moment, for example, some AI processing spikes, our platform is going to stay the same. And with some building recovery and automated recoveries and backups, we're able to keep offering for our customers a platform that is going to be stays all the time for all of our customers. And finally, the other thing I like to share with you is the use of RabbitMQ. Basically, by queuing all of our AI have process, we're able to make all of this processment and keep offering for all of our customers a platform that is going to keep smooth and at the same time responsive.
Thank you. It's impressive how much you can achieve with such a linear footprint. Atakan, technically speaking, how does you utilize Hyperdisk ML, as you mentioned? How does mounting that Hyperdisk ML as read-only access across thousands of pods eliminate your I/O bottlenecks without changing the application logic underneath?
Okay, the key point is to avoid copying the same model to every pod, right? And instead, we stored the model once and moved into cloud storage and hydrate it into a hyperdisk volume and mounted it as read-only across all pods. So many pods can access the same model at the same time now, and this removes the I/O bottlenecks and allows us to scale much more efficiently, right? And honestly, at first, this was manual for us, but tools like GKE volume populator, it became a push-button operation, which is good. And we didn't change our application logic layer. I think this is important for us because making changes to the app logic could create many issues, right? Many edge cases. And with this solution, we only changed the write layer, correct layer, the storage layer, and tested only that part. After our tests, we deployed the system to production, and we saw that our problems were resolved. So I think I also summarize the technique part, right?
Thank you very much for sharing that. I think today we have covered a lot of ground, from spot instance optimization to AI model hydration. I think with that, you can continue your learning journey across the next 2 days. These are some of the sessions that are related on the computing infrastructure side with GKE, GCE, and Hyperdisk. Also, please take a moment to complete the survey if you like this format, evolve and improve with every next. Thank you, everybody, for taking the time, and have a great rest of your next. Thank you.